Hello, everyone. I'm very sorry that I can't be with you all today, but I am very happy to be able to give you this talk electronically. I would like to start by expressing my deepest appreciation for being awarded the PAC Award, Research Award for polycyclic aromatic compound research, and especially the wonderful words in the announcement of the award for the work we've done here on PAHs and PACs. It is a great honor for me to have been given this award by your group, because over the years I've come to respect the polycyclic aromatic compound group community very highly, because I'd always turn there to find out all the marvelous things that PAHs and related compounds were doing in so many applications in parts of our daily lives and world. The breadth of the reach of the PACs is really an incredible thing. I also want to especially thank Ivan, who took on not only the very difficult job of organizing a meeting, which is always an incredible task, but also to put in all that extra work to make this presentation possible. So thank you, and now I'd like to get started with the actual presentation. The first slide shows 3 galaxies in our local neighborhood to the Milky Way, our own galaxy, the Milky Way. These are spread across the universe, but not too far from us. And what you'll see in these slides, for example, on the top left, the peculiar shape. All 3 of these things look quite different. And what you're seeing is a combination of the visible image taken from the Hubble telescope and the infrared image taken with the Spitzer Space Telescope that was launched some 10, 15 years ago. The visible part is the blues and the kind of gray hazes. And the incredible thing when these pictures first started to come back was that the PAHs were attracted by these red images, and people were just staggered. It was just an unbelievable surprise, and this was as I said, 10 years ago now. This galaxy in particular is really amazing. It looks like a cigar in the all visible images, just a white little band of light. And what's being shot out from the middle of that thing are PAHs. And in this case, the PAHs are not only internal to a galaxy, but now they're extragalactic PAHs as well. So the story of the PAHs has just been an incredible one. And how did we get to this point where we can look at a picture like this and really start to understand things? But by the end of the talk, you'll realize we need to learn a lot more about the properties of PAHs before we can extract the information these kinds of pictures and the spectra that are hidden in them reveal. So how did we get to this point? Astrochemistry is a young field. For most of you in the audience, perhaps you don't remember these big dates. Back in 1963 is the first discovery of an interstellar molecule, OH. Up until that time, space was considered to be chemically barren through most of the 20th century. And it was this discovery of the simplest of things, ammonia, formaldehyde, and CO, that the spell was broken. This was all through the 1960s. And you can see that these are quite simple things, but believe me, they made news all over the world. The discoverers of these things were on the cover of Time magazine. And it just really changed the fundamental picture of what was out there in space. Prior to that, it was known it was very, very cold in deep space and a lot of UV from all of those stars, so these things shouldn't have survived. And to underscore the shock of it all, look at that last sentence. Polyatomic molecules containing at least 2 atoms, other than hydrogen, form in the interstellar medium. That was the headline. So where did they find these things? If we look on this next slide, interstellar molecules were found in what is called dense molecular clouds. What you're seeing here in the lower quadrant is a picture of the visible picture taken by Hubble of a molecular, what's now called a molecular cloud. They used to be called dark clouds. And where you are in Sweden right now, if you look up at night, unless it's too close to the Arctic Circle, when the night gets dark, you'll see beautiful stars, a very dense pattern of stars, but you'll also see these dark patches. They're not holes, but they are these so-called dark clouds, and they're comprised of little dust particles, tiny things, 1/10 of a micron in diameter. But there are a lot of them. In the astro speak, it's a dense cloud because these things are light years across, whereas in reality to us, there might be one dust particle in the size of the, in a room the size of the room you're probably in now, a basketball court or so. So it's just because the clouds are enormous, there are all these dust particles, they shield the UV light, and it's in these dark clouds that these simple molecules are forming. So when infrared astronomy was born, and that was a little bit later than the gas phase molecules were all measured using microwave and radio frequencies. It's rotational spectroscopy. And that was developed in the 30s and 40s as an outcrop of radar, the invention of radar. But it wasn't until the 60s that infrared astronomy barely started, but by the 70s, images were being able to be taken and measurements were being able to be made in the mid-infrared wavelength region, which for the chemists in the audience is the region where molecular signatures are found. So when they started to turn on the same exact cloud in the lower left at a frequency for which the PAHs were emitting, this is what they saw. The entire cloud was covered in emission from polycyclic aromatic hydrocarbons. The emission followed the shape of the cloud, and it really is the interface between the cloud and the harsh radiation of the interstellar field. So how did we get here? And how does this fit in? This is all very nice. Now there are lots of PAHs out there, but are PAHs really that important? What do they do? Well, it turns out during the same time, the development of the field, this shock happened over and over again. This is the life cycle of organic carbon in the interstellar medium. And what you're seeing here is the cycle between, and we'll start at the stellar death stage. When the stars burned up all of its hydrogen and helium and it's made all sorts of heavier atoms, some stars have more carbon than oxygen, and these start to puff out enormous quantities of dust and carbonaceous molecules. Then these molecules float around in space once they're far away. This is called the diffuse interstellar medium. And when enough shock waves and supernova blasts or whatever happen, these things start to get collected and start to form darker, dense clouds because of the dust obfuscation of the radiation. And then with time, if you look at the little bright thing below the Horsehead Nebula, a star will be formed by the compression. The dust will start to collect, but one particle will stick to another, and eventually you'll get a nebula from which the star is forming, and what doesn't go into the star becomes the planets and the rest of the story. And so then you go, but in these regions where the stars are irradiating the cloud, a lot is going on, and we'll talk about that in a minute. Eventually you get back to a stable system that we find ourselves in, and then once the star burns its simple fuel, the process goes on again and again. And what was found, every stage of these things with these spectra, and you'll notice there's a 7.7 feature, a 6.2 microns, and that's 1,600 wave numbers for the real chemists, and the 1,300 wave number region. And so this is the same spectrum, and that was really the surprise. What could this be? Because now it's all over the place. It's at every stage of stellar evolution. What are these are great, could be new probes of the medium, but what are they telling us? Or are they just saying PAHs are there? So that's when the interest started to really try to understand what these spectra were telling us. And in the early days, back in the 70s, this is what we saw. The top spectrum in all of these is the interstellar spectrum, emission spectrum, and these are compared to the spectra of PAHs embedded in salt pellets. And you'll see the comparison is crude, but satisfactory to suggest this is the kind of stuff that might be out there. But it was also clear these were not good enough. So this showed there was a growing need for laboratory data taken under astronomically relevant conditions, and that gave birth to this whole field of lab astrophysics. Gone were the days when Edwin Hubble or George Lemaitre, the person who suggested the Big Bang Theory, could mine the data of a previous century of spectroscopy on atomic hydrogen and discover an expanding universe, open or closed, that is some 15 billion years old. We needed new data, and we needed new data desperately. That's what we started here at Ames. This is one of the first spectra we succeeded in getting of an isolated cold PAH ion. The PAHs are ionized into interstellar medium because of the UV fields that are floating around. And the fact that they hang around much longer than these other small species is because they are tough customers. And the other thing to realize is that given the radiation field, the PAHs that are out there probably have the majority of the family of emitting PAHs is between 50 to 100 carbon atoms. So these little ones, 2, 3, 5, 6 rings, won't survive probably up to cornene or ovaline, that's 24 or 34, 2 carbon atoms. And then interesting chemistry takes place. But this was the beginning. And as time went on, Doug and the group started to measure more and more spectra. And what we found is many had nice bands that filled in the interstellar emission spectrum, which is shown on the top here. By 1996, we had, this type of a match, if it's not, this type of similarity. And of course, every pH we measured did not have these features, so it was beginning to tell us what kind of structural information, and so it was important. And by 2000, we had this kind of match, and it was really getting very good. This took about 30, 35 PAHs to make that match. But what was interesting, if you showed this to an astronomy audience, they'd always pick on the mismatches rather than the incredible similarity of the spectrum. But that didn't deter us. We kept plowing on. And as we accumulated more and more data, it's clear we couldn't get our hands on the larger molecules, the ones that are probably out there. And this is one of my pleas to people in this audience. And I will sum up near the end the kind of information that you may have available that could be used to push this field forward. So eventually we depended on DFT calculations. Charlie Bauschlicker here at NASA Ames is a well-known computational chemist, and he did a heroic job in computing the infrared spectra of an enormous number of these things. And so now we have the wonderful NASA Ames PAH infrared spectroscopic database. It's a website. It was put together by Christian Boersma, a PAH spectroscopic library now that has over 1,000 spectra in it. And then IDL and Python suites so people can download them, use the data, handle the thing spectroscopically. It's a little bit of a treasure chest of spectra with nice tools. You can go through and see the vibrational modes, what the symmetries are, and so on and so forth. It's been downloaded now all over the world, and not only by astronomers, all kinds of folks are using it. So it was a lot of fun to get this far, and now we're continuing to work on that. And why all this effort? Well, we now know that PAHs are the single largest source of accessible carbon in the universe, in the cosmos, as far as we can see. They contain some 20% of the cosmic carbon. It's an enormous reservoir of carbon. They convert interstellar ultraviolet radiation to infrared radiation, and they account for 30% of the galactic infrared emission. They're, again, a huge amount of energy conversion. Large PAHs contribute to the ionization balance and thereby coupling of the magnetic fields to the gas in which they're in. What that means is that since they are easily ionized, 6, 7 eV, the highest energy photons out there go up 10, 12 eV. So these things are ionized. The PAHs eject electrons. The hot electrons heat the gas around them. The PAHs align with the magnetic field, so when dust and whatever comes moving through, or the gas, they either break and slow down the collapse, or if the field lines get tighter, they'll accelerate the collapse. And so, believe it or not, they are important players in cloud collapse times, and cloud collapse times are what form stars and planets. Another thing they do besides that and heating the medium is they have a lot of surface area, and formation of H2 on the surface is a big contributor to the amount of the molecular hydrogen to atomic hydrogen ratio. So they're very, very, very important. And now the next slide shows, continues on this theme of why all this effort. And given that PAHs are so widespread, they probe many, many different astronomical environments. If you recall those pictures of the galaxies, you can see they light up in one part, but they don't light up in another part. They trace the spiral arms in the spiral arm galaxy, but they look like a frisbee in another one. And then other regions, they're blowing out into intergalactic space. So if we could understand why they are there and what the information is contained in their spectra, we'll be able to really use them as powerful new astronomical probes of conditions in these other regions, in all of these other places. And the third point is this is important right now because NASA is going to launch a new telescope in the next couple of years, we hope, the James Webb Space Telescope. Its cost now has run up to almost $10 billion. And it's all in the infrared. It's an enormous thing, and it will be able to capture for the first time the complete mid-infrared spectrum. And of course, if it's looking at one of these PAH-emitting regions, it will give the first full PAH spectrum. With a small single aperture, that means it can go down, follow a pencil point of light to a very small part of space far, far away. In principle, it should be able to see across the entire universe. That remains to be seen. And that will tell you when the horizon for the formation of carbon happened back a long time ago. And it will fully resolve the PAH bands as we know them. These bands are not nice gas phase lines that need very high resolution. They are vibrational emission bands. They have certain lifetimes, and that determines the bandwidth, and you have the whole bunch of PAH bands piling up on top of one another. So it's not a simple one molecule kind of spectroscopy. But nonetheless, they'll contain a treasure of new information that we simply cannot currently address. So with this, I'd like to stop the section now on spectroscopy and move on to the challenges in a couple of other areas. And the first has to do with the formation of PAHs and growth, PAH destruction, and PAH isochemistry. PAH formation and growth has followed the model of combustion, soot formation, and so forth. And the reason for that is because, as I said earlier, if we look here at the beginning phases of the carbon life cycle, and when the star's in its dying stages, it's ejecting a lot of carbon, a lot of simple molecules, and then these things coalesce and react. And then once they are formed, everything that star has ejected moves out into the diffuse medium where the things are starting to be, the simpler ones are being destroyed. Then eventually they're trapped in a cloud. And when stars form in those star-forming regions, the PAHs are evaporated from the dust, and and then they become visible again, and then they're starting to erode. And a lot of chemistry takes place, not to mention what happens when the PAHs fall on planets and comets. So the next slide shows the beginning of this cycle right here, what we think was going on. And I'm very happy to say in the last few years, brave experimentalists have actually looked into this beyond just theoretically talking about it. On the left, you'll see a picture of a spectrum, in the high-resolution spectrum taken from the ISO satellite of the gas phase from one of those late-type stars that's ejecting carbon outfall. And you'll see it's full of C2H2 acetylene, CN cyanides, various carbon chains, and there was even a little potential detection of one line of benzene. On the right is the larger picture of the stellar evolution, the ejection and the evolution of stuff from simple molecules to particles to larger molecules, PAHs, and then eventually particles. So the next slide shows that picture in some detail. Let me get my light on this thing. This is the first step, and many of you know this already very well. You've probably had your careers in this part in the green box. And this is a study of the addition of cyanide to a simple diethylene molecule to the formation of the first ring. And I don't want to spend too much time on this. I think this audience knows these things very well. The point of these slides is that there are experiments now that are looking into these things step by step. And it will move along that carbon evolution. And here again, the addition with the green, there's a bay region there, and the green arrow is indicating at the addition of acetylene across that, and you'll start to build a multi-ring system, getting further and further now to eventually things will start to move into clusters and particles. And there's even some beautiful cluster work now available, where one of the surprising results is this little tri-molecular cluster of 3 same PAHs. Once it hits UV, they start to cyclize more larger, but also curve up, which leads to the question about fullerene formation. So this would be bottoms up. This is one route to make the fullerenes, which have been detected out there a few years ago, from simple PAHs. And in this case, these are larger PAHs that were available for a short time, and they can be photo-destroyed and become members of the fullerene family. So this part, the growth now is at least starting, and as I said, these species are all far, far too small to be relevant for the space situation, except for the fullerene formers. But it's a step forward, and every one of these individual steps that have been found was not consistent with the theories up to that time. So what we need data on is larger PAHs and all of these processes that take place to make them grow and to have them destruct. What is their pathway to destruction? And here I'll just have two. I'll focus only on the one on the left. If the PAHs are large enough, the fragmentation pattern is one in which H and H2 loss are the first steps. So these things can actually be contributing, as I mentioned earlier, to the amount of hydrogen, molecular hydrogen in space, and determining the H2H2 ratio, as well as on the right here, I'll briefly mention, they also form smaller, once they get below a certain size, they fragment, and they might actually be part of the feedstock for those smaller molecules people are seeing in the gas. So the whole story now is emerging. PAHs are not just present at all of these things. In a way, because of their infrared emission spectrum, they are witnesses and can tell us what's going on. Plus, they are also playing active roles, apparently, in many different ways in these various environments. So now what I'd like to do is go from these things now have gone through the diffuse medium, condense into a dense cloud. As I said earlier, this is where those molecules were found in the dark reaches of the cloud. And this is a visible picture. If you saw this in the PAH band of that Spitzer satellite, that Horsehead barely sticks up above the pi emission C. But again, the spectra are all so similar, and that's why you need to get into the details to see what's going on. So now what happens if the PAHs are inside the clouds where the dust is very, very cold, and in regions of star formation where the stars are close to the edge of the cloud, or a star is actually formed, the dust in that area gets really irradiated very, very strongly. So this is a really nice picture of this evolution of these things, the dust particles. These things, remember, are teeny tiny. They're not the size of planets. Submicron usually, and they could either be silicates or they could be carbonaceous little chunks of carbon. The cores that are cold, they're on the order of 10, 20 Kelvin, maybe 30. Anything floating around in the gas that hits it obviously will stick, and that includes the PAHs. Things get irradiated, photochemistry takes place, and larger molecules are formed, combinations of the simple species with the aromatic species, and you have a real mess. But astrochemists have only, in the last 4 or 5, I'll be more fair, 10 years, accepted the inclusion of grains into the chemistry. It was all done in their models in the gas phase, or maybe 20. But they're very reluctant to put PAHs in because it's going to be the Wild West all over again. So, but here there have been a few brave groups trying to study this stuff. So about 20 years of photolysis studies of PAHs and low-temperature ices, and these are water ices, water-rich ices, because water is the most abundant ice form out there. The ionization energy is lowered by 2 electron volts. So suddenly this simple little ice, the chemistry is not just photochemistry, non-ionized chemistry, but now you have ions floating around in there. Opens up a lot of other processes. PAH ions were surprisingly stable, are easily produced. You see the ion bands, as soon as you turn on the light, and you'll see them even with 300 nanometer radiation. And they remain trapped in the ice up to temperatures near 100 Kelvin. When the bands start to disappear and then reactions start to take place. The other thing to note is, again, hydrogenated PAHs and oxidized PAHs are important photoproducts as well. And here's a slide that's probably 25 years old now, in the early days, where if you photolyze benzo-GHI-parylene in water ice at 10 Kelvin, you'll start to see this whole family of structures being formed, and this information came out of the mass spectroscopy, mass spectral studies. Very recently, we have some wonderful work in a few groups where they actually identify, using infrared DFT calculations, what exact kinds of addition reactions occur and where they occur on the molecule. And so now we're really ready to put the thing together. Let's look at one of those regions right here. This is a dense cloud, the edge of a dense cloud, a Hubble picture. What this little square is a square taken by where the Spitzer Space Telescope measured infrared spectra at each one of these little pixels. And this is what in this region between the cloud where the PAHs and gases things are coming out of the cloud into the UV-rich zone, and there's a star right down there. So now we know of these places, and we have these kinds of data. There are 300 spectra in that cube. And so you can see the challenge that's in front. Lots will be going on, destruction, growth, and so on and so forth. And we need to be able to analyze these spectra. And the last slide before my conclusions is the very, very, very big news that Brett McGuire, the Harvard Smithsonian, and the radio telescopes in Greenbelt, finally discovered the first aromatic molecule in the gas phase about a year ago, benzonitrile. And what I just heard from him a couple of days ago at a meeting, They've also found 2 of the cyanonaphthalene isomers in the same molecular cloud. This is going to break the dam open, and there's going to be a flood now. Once, instead of people saying, well, it looks like the infrared says there are PAHs out there, but we never found a single one. Well, now we've got end members. Here's benzene and fullerene on the other end. So it's good enough to call those PAHs in astrophysics. And naphthalene is a bicyclic PAH, but the polycyclics won't take long to find. So let me finally come to my conclusions. The main thing, there are 3 takeaways: that we really need help in all of these regions. In the infrared, we are really not ready for what JWST will give us. The second point is about PAH formation and growth and destruction. We need to study much larger molecules. And then third, in the PAH ice chemistry, that's just a beginning, because the ices now are recognized as very, very important species to be playing in the cloud chemistry. And if you put PAHs in those ices, that will change a lot of the results we've seen so far today. So my plea is to those of you in the audience, thank you very, very much for your attention. And if you're working in any of these areas where you are interested in maybe dipping into this crazy problem, please contact Ivan. He'll give you my email address. And while I'm not active in a whole bunch of this stuff anymore, but I'm still working in the infrared part, I will make sure your interest is I connect you with the people who I know are doing really good work and willing to go ahead. Again, thank you very much, and I'm really sorry I'm not there. It would have been wonderful. Have a wonderful meeting.